Okay, so far we have done the concepts of acids, bases, and the theory related to them. That is Arrhenius theory, Lewis theory, and the Lowry-Bronsted theory. Now, based on all this, let us try to understand the ionization constant of water and its ionic product. That is, we are talking about 6.11.1 section. Water is considered as a weak electrolyte, and therefore water has a tendency to dissociate also. So when it tries to dissociate, it is going to produce H plus and OH minus ion. The first water molecule provides H plus to the second water molecule, and therefore you will be left out with OH minus from the first, and the second molecule will become H3O plus. Now, the water in the reactant side is liquid, whereas the hydroxide ion and the H3O plus ion both are aqueous. I hope you have understood this. The first molecule of water is considered to be dissociating to produce H plus ions and OH minus ions. So can we say that this is an acid because it is going to give a proton? The second molecule accepts the proton, so this acts as a base. For this acid, the OH minus is the conjugate base, and for this base, the H3O plus is the conjugate acid. This is in accordance with the Lowry-Bronsted theory. Now, since the water is a weak electrolyte, we can assume that it will also attain equilibrium, and at the state of equilibrium, the ratio of products to the reactant again becomes constant. Okay, so let us write the expression. The product of the product concentration, right, by the reactant, product of the reactant concentration. Now, in this case, the reactants are in liquid state, and the change in the concentration is ignorable here since it is liquid in state. So, while writing the equilibrium constant involving pure liquids and pure solids, we will ignore the or we will take them as 1. So, your equilibrium constant for this particular process will be equal to the product of the OH minus ion concentration and H3O plus ion concentration. In simple, we can also put it as OH minus ion concentration into H plus ion concentration, because we know that H plus ion is nothing but the H3O plus ion. So we can just, for simplicity, substitute the H3O plus ion concentration with H plus ion concentration. Now, since this equilibrium is about the dissociation of water, we can also call the equilibrium constant as Kw. So the Kw is now called as the ionic product of water. Okay, so it is nothing new. It is equilibrium constant for the dissociation of water as a weak electrolyte. So it is same as Keq, K, C, K, P, etc. Yet another term which is called as Kw. Now we know that equilibrium constant value is fixed at a given temperature. For the water, the equilibrium constant or the ionic product of water, that is Kw's value, at 298 Kelvin happens to be measured as 10 to the power minus 14. So Kw at 298 Kelvin. We know that for every reaction, the equilibrium constant at a given temperature is a fixed value. So since the dissociation of water is also, or ionization of water is also uh, establishing an equilibrium, the Kw, which is nothing but equilibrium constant for this process, should also have some value depending upon the temperature. So at 298 Kelvin, the Kw or the ionic product of water happens to have a measure of 10 to the power minus 14. So if you substitute this value into the equation, what we get is 10 to the power minus 14 is equal to the product of H plus ion concentration into OH minus ion concentration. Now, if you go back and see, whenever water dissociates, the amount of OH minus ion concentration will be same as the H plus ion concentration. So, in this equation, the amount of H plus ion concentration is same as OH minus ion concentration. So, can we not write it as H plus ion concentration in the place of OH minus ion concentration? We'll put it again as H plus ion concentration is equal to 10 to the power minus 14. So can we write it as H plus ion concentration square is equal to 10 to the power minus 14, or in simple, the H plus ion concentration in water is square root of 10 to the power minus 14, or in other words, this is nothing but 10 to the power minus 7. So we understand that at 298 Kelvin, whenever water breaks down to form H plus and OH minus ion concentration and attains an equilibrium, the H plus ion concentration will be 10 to the power minus 7 moles per liter, and the same is the OH minus ion concentration, which is 10 to the power minus 7 moles per liter. Okay, now after understanding this, let us try to arrive at the pH of this water. So what is meant by pH? pH refers to negative logarithm of the hydrogen ion concentration. So the pH of the water would be minus of log of 10 to the power minus 7, which is the hydrogen ion concentration. And we know that log of 10 to the power minus 7, or when we apply log of a to the power x, it has to be written as x log a. Applying this concept here, it will become minus of minus 7 log of 10, and log of 10 happens to be 1. So the pH of the water at 298 Kelvin would become 7. I hope this is understandable. In your class 10, you would have studied that pH of water is 7. But here you have to understand that pH of water is 7 only at 298 Kelvin. So it is temperature specific, because if you go back and understand, the 10 to the power minus 14 value of Kw happens to be at 298 Kelvin. We know that it is nothing but equilibrium constant. If you change the temperature, this value will also change. And as you substitute here, the square root of a different value also will be a different value. Let us just hypothesize that at a different temperature, it is, say, for example, at around, I'm just taking an example, say at 310 Kelvin, the Kw is measured to be 10 to the power minus 12, which is an extreme case. I am just taking it for the simplicity. So Kw happens to be 10 to the power minus 12. What is meant by Kw? It is product of hydrogen ion concentration into OH minus ion concentration. Whenever water dissociates, we know it produces equal amount of H plus and OH. So I can also put it as H plus ion concentration into H plus ion concentration is equal to 10 to the power minus 12. What did I do? I replace the OH minus ion concentration with H plus. In other words, H plus ion concentration is equal to 10 to the power minus 12, and H plus ion concentration will become equal to 10 to the power minus 6, which is square root of 10 to the power minus 12. Now, if you take the pH, which is negative logarithm of hydrogen ion concentration, it will be minus log of 10 to the power minus 6, and which will give me 6. So it is possible that at a different temperature, water is neutral, but its pH may be not 7, it may be less. I hope you understand this. So the concept that pH of the water is 7 is applicable only at 298 Kelvin. At a higher temperature, the pH value may come down. Okay. Now we can arrive at some more expressions. What are they? Kw is equal to H plus ion concentration into OH minus ion concentration. I can take log on both the sides. So this will give me log of Kw is equal to log of H plus ion concentration plus log of OH minus ion concentration. How did we get that? We know that log of A into B will become log of A plus log of B. So we have applied this only. When I apply log on both the side, log of Kw, log of the H plus into OH minus can also be written as log of H plus log of OH minus ion concentration. Let us introduce negative sign throughout. So when I introduce a negative sign throughout, I can put it as PKW. What is P? P generally refers to negative log. So negative log is written as P. So PKW is equal to negative log of H plus, which is nothing but pH, plus negative log of OH minus, that means POH. So this is yet another term. PKW is equal to pH plus POH. What is PKW? Negative log of 10 to the power minus 14 is equal to pH plus POH. When I take negative log of 10 to the power minus 14, I'll be getting 14. So yet another useful term, useful expression would be that pH plus POH is equal to 14. Okay, another expression that may be useful will be Kw is a product of H plus into OH minus ion concentration. So supposing you have been given OH minus ion concentration, you can easily find out the H plus ion concentration using this relationship. For example, somebody tells you that uh, the concentration of NaOH aqueous is 0.01 m, and you are asked to find out the pH of this. You are asked to find out the pH. What would you do? NaOH concentration is 0.01, or in other words, OH minus ion concentration is 0.01 m, or it is 10 to the power minus 2 m. Now, for pH calculation, I would need the H plus ion concentration. So I'll substitute the OH minus ion concentration in the expression and the value of Kw. Kw is 10 to the power minus 14 at 298. So H plus ion concentration into the OH minus ion concentration is 10 to the power minus 2. So we'll take that. The H plus ion concentration would become 10 to the power minus 14 by 10 to the power minus 2. Therefore, this will be 10 to the power minus 12. What we are left out was 10 to the power minus 12. Now let us take the negative log of H plus, which would actually give me the pH. Negative log of H plus ion concentration from here is 10 to the power minus 12. So this will be minus of minus 12 log of 10. In other words, the pH of this NaOH solution would become 12. Right? So I hope this ionization constant of water and its ionic product, the pH scale, etc., is quite clear to you. Let us just look at one of the problems, which is 6.16. Example problem 6.16. Okay, what is 6.16? It says that the concentration of hydrogen ions in a sample of soft drink is 3.8 into 10 to the power minus 3 m. What is its pH? So they are saying that soft drink has uh, the concentration of H plus as 3.8 into 10 to the power minus 3 m, and they are asking you to find out the pH. So it is as simple as negative logarithm of H plus ion concentration. You substitute the H plus ion concentration as 10 to the minus log of 3.8 into 10 to the power minus 3. So in exam, they would be providing you the log value of the 10 log of 3.8, etc. So when you calculate and get the number, that can be expressed as the pH of this soft drink solution. So you can see some steps written. I'll try to explain that also. So let us apply this negative of log of 3.8 plus log of 10 to the power minus 3. We know that log of A into B is log of A plus log of B. log of a to the power x will be x log a. So this would become negative log of 3.8 minus 3 times log of 10, which is because of log of a to the power x is a x log a. Log of x to a to the power x will be x log a. So log of 10 is anyway 1. So when you solve for this, you would be provided with log of 3.8 value. When you solve for this, you would be getting the answer as 2.42. So it tells you that the pH of this soft drink is indicating that it is acidic. Now, most of the calculations are understood to be done at 298 Kelvin. Unless they mention a special temperature, you will consider that it is 298 Kelvin only. Okay, to understand 6.17, we will have to understand another concept called as common ion effect. Okay, common ion effect influences, it's an application of Le-Chatelier principle to the equilibrium. We know how the Le-Chatelier principle directs the equilibrium to go in the forward direction or in the backward direction, depending upon the changes made in the concentration. So here also it is the same. Okay. So what is common ion effect? Assume that you have got a weak acid, and weak acid exhibits equilibrium situation. So assume that we have got CH3COOH in dissociation to form CH3COO minus and H plus. Now, whenever you write such an equation, we should also know to write how we should also understand how to write the concentration terms of the reactants and products. So we'll assume that I took 1 mole initially at T is equal to 0. We know equilibrium takes up some time to set up. So at T is equal to 0, assume it is 1 mole. The amount of acetate and H plus would be 0. After the setting up of the equilibrium, since it is a weak electrolyte, we'll assume that out of 1 mole, alpha mole is dissociating, wherein alpha value is very, very, very small compared to 1. Why? Because it is a weak acid. So 1 minus alpha is the left out acetic acid. We can assume that alpha has undergone dissociation. So if alpha has undergone dissociation, you should be getting alpha moles of acetate and alpha moles of H plus. Okay, once again, if I take 1 mole of acetic acid, initially there is zero amount of acetate and H plus. At equilibrium, if alpha moles out of the one dissociated, it should be producing alpha moles of acetate and alpha moles of H plus. So the amount of acetic acid left out would be 1 minus alpha, acetate would be alpha, and H plus would be alpha. Now, supposing the concentration is not 1 mole, instead it is 5 moles. So what we will do? Multiply the entire thing by 5. So this also will be multiplied by 5. So this will be multiplied by 5. This will be multiplied by 5. Similarly, I will just take up a general expression for the concentration and say that it is C moles per liter. So this would become C times 1 minus alpha, C alpha and C alpha. Okay. So this is something which you will have to do for every equilibrium. C times 1 minus alpha is the left out acetic acid. C alpha is the acetate ion and C alpha is the H plus ion. So it's very useful. Do not ignore it. We will be using this a lot to do the pH calculations. Okay, once again, coming back to common ion effect. What is common ion effect? Where a weak acid dissociates to very less extent and the extent of dissociation is very small. I told you out of 1 mole, only alpha dissociates, and that alpha is also very, very small, very small. Now, to this established equilibrium, I am going to add from outside some amount of HCl. I'm going to add a strong electrolyte like HCl. When I add HCl, it will produce Cl minus and it will produce H plus. So the equilibrium will sense that the concentration of H plus has gone up. According to Lee-Chatelier's principle, when the concentration of one of the product increases, the reaction goes in the backward direction. When it goes in the backward direction, we can think that already the acetic acid was dissociated to very small extent. Whatsoever dissociation occurred, even that is decreased because of the reaction moving in the backward direction. What would happen when the reaction goes in the backward direction? Whatever little H plus and acetate were formed, from that the H plus will combine with the acetate ion to go back and sit as acetic acid. So now, after the addition of HCl, the degree of dissociation, can we assume it is a different value Y? This Y is much, much, much less than alpha, which is much, much, much less than the original concentration of 1. You understood? So when acetic acid is taken, alpha moles out of 1 dissociated. But when a strong electrolyte like HCl is added to the existing equilibrium, the reaction is made to move in the backward direction due to increase in the concentration of H plus. This decreases the degree of dissociation furthermore. Okay. So let us now define the common ion effect. What is common ion effect? The suppression of degree of dissociation, suppression of degree of dissociation of weak electrolyte by the addition of a strong electrolyte which provides a common ion to the equilibrium. Okay. Now, my question is, supposing there is an equilibrium. Okay. CH3COOH is in equilibrium with CH3COO minus and H plus. To this existing equilibrium, will there be any effect if I add NaCl? The NaCl produced will produce Cl minus ion and Na plus ion. Now, because of addition of NaCl, neither the acetate ion concentration is increasing nor the H plus ion concentration is increasing. So, the equilibrium remains unaffected. When will the equilibrium be affected? If you have added some electrolyte which provides a common entity. So, let me take another example. Let me add sodium acetate. When I add sodium acetate, this time it produces CH3CO minus and Na plus. This seems to be the common ion. Suddenly the equilibrium will feel that the concentration of acetate has gone up. This will prompt the reaction to go in the backward direction. Alpha was already very, very small. Because of the reaction moving in the backward direction, the degree of dissociation alpha is further suppressed to a low value of it, which is low Y. So in the presence of common ion effect, the degree of dissociation of a weak electrolyte is further suppressed. So if it was dissociating to the extent of alpha, it is dissociating much less, which is represented with Y. So suppression of degree of dissociation of weak electrolyte by the addition of a strong electrolyte, which provides a common ion to the equilibrium, is said to be common ion effect. Okay, so based on this only, we have our next problem, 6.17. Now in 6.17, example 6.17, the question says you have to calculate the pH of HCl solution whose whose concentration is 1 into 10 to the power minus 8. Okay, whose concentration is 1 into 10 to the power minus 8. Now, what is the problem with this? Let us try to understand. HCl's concentration is 1 into 10 to the power minus 8. That means the H plus concentration is also 1 into 10 to the power minus 8 because it is a strong electrolyte, it will dissociate fully. But how much H plus are you getting? 1 into 10 to the power minus 8. Let us try calculating the pH, which is negative logarithm of H plus ion concentration. So it is negative logarithm of 1 into 10 to the power minus 8. And when you solve for it, it will give you result 8. And I told you all these calculations are done assuming that the temperature is 298. So can pH of water, can pH of, sorry, HCl being an acid, can HCl being an acid have a pH of 8? Will it not indicate that the pH is more than 7? Will it not indicate that it is a base? Is it possible for water carrying even little amount of HCl, right? Because the concentration seems to be very less. So can you imagine that water carrying even whatsoever little amount of HCl, can it ever become pH 8? Won't it indicate that it is a base? But HCl is actually an acid. So something, somewhere we are missing. Okay. So what is it that we are missing? So this is not how we should do this sum. When the H plus ion concentration is so low, we cannot do it this way. Why? We know that HCl dissociates to form H plus and Cl minus, and the amount of H plus is 1 into 10 to the power minus 8 m. Whereas water, being a weak electrolyte, dissociates to produce H plus and OH minus ion concentration, where the H plus produced by water is 10 to the power minus 7. OH is also 10 to the power minus 7. Now, the H plus coming from the water is more than the H plus coming from the acid, right? So when the H plus coming from the water is more, it cannot be ignored as compared to uh, uh, that is, it cannot be ignored against 10 to the power minus 8. See, we have done one more problem here. Look at this problem. The H plus of the soft drink is 3.8 into 10 to the power minus 3. So soft drink obviously will have water in it. And when water dissociates, it will produce H plus and OH minus ion concentration. There also it was 10 to the power minus 7. So the H plus produced by the soft drink is much, much, much more than H plus produced by the water. So the water's contribution is ignored because the H plus produced by the soft drink is more, which is 10 to the power minus 3, which is quite large, than 10 to the power minus 7. We are ignoring the contribution of water. But in this particular problem, the H plus provided by the water is more and the acid is less. So you can never ignore now in this situation, you cannot ignore the H plus contributed by the water. Okay, there are two equations going on, and only the second equation happens to be the equilibrium. So we can write the equilibrium for this only. So we can put it as H plus ion concentration into OH minus ion concentration. And since it is about water, we'll put it as Kw. And what is the Kw's value? 10 to the power minus 14. Now, how much H plus do you have? You have, okay, but before we are going into that, this situation happens to be a common ion effect situation. See, water was dissociated to very less extent. Okay, the alpha, the degree of dissociation of a weak electrolyte is very, very less. To this, we are adding HCl, which is a strong electrolyte. What would happen? The degree of dissociation of the weak electrolyte will further decrease. So it will no longer be 10 to the power minus 7. It will be, in fact, lesser than that. So the amount of H plus produced in the presence of strong acid is further lesser than 10 to the power minus 7, but we don't know what it is. So we'll assume it is X. So if H plus is X, the OH minus is also X. I hope you have understood this. See what I told you. That's why we did common ion effect description here. To the weak electrolytes dissociation, we are adding a very little amount of HCl, but we know HCl is a strong acid. So H plus concentration is coming from both water as well as HCl. So in the equilibrium senses that there is more H plus than the usual, which pushes the equilibrium in the backward direction. That means suppression of degree of dissociation takes place. So if it were only water and no HCl, the amount of H plus coming from the water would have been 10 to the power minus 7. But now, since you have H plus coming from acid also, the degree of dissociation of water decreases to a smaller value, which we don't know how much. So we are assuming that it is X. If H plus is X, OH minus is also X. Now let us substitute it in the Kw. Why we are still using the Kw equation? Because out of the first and the second, only the second is an equilibrium process, for which we can write the equilibrium constant. So the H plus is coming from both HCl and water. So how much it is? It is X plus 10 to the power minus 8. X coming from water and 10 to the power minus 8 coming from HCl. The OH is still coming only from the water, which is only X. Fine. Now this, if you solve it, it happens to be X square plus 10 to the power minus 8X. Okay, so it becomes a quadratic equation and you will have to solve this equation, right? When you solve this equation, what will happen? You will get a value of X, okay? And that value of X happens to be 9.5. I'm just writing it from here. 9.5 into 10 to the power minus 8. What is this X? This X is the amount of H plus coming from water. But what is the total amount of H plus? The total amount of H plus happens to be 10 to the power minus 8 plus 9.5 into 10 to the power minus 8. So you sum it up and take negative logarithm of it. When you sum it up, what is this? 1 into 10 to the power minus 8. 1 into 10 to the power minus 8 plus 9.5 into 10 to the power minus 8 will become 10.5 into 10 to the power minus 8. So take negative log of H plus. Here also you take the negative log and what you get here will become 6.98. So pH of acid whose concentration is 1 into 10 to the power minus 8 m is not 8. Instead it is still less than 7, just less than 7. And why it is less than 7, just less than 7? Because the acid HCl concentration is very, very, very small. So it has to be in acidic range, but since the concentration is very less, it's just less than 7, 6.98. I hope you have understood this problem, right? So in the next video, I will discuss about the ionization constant of weak acids and weak bases.